All right, so what we're looking at this one is section 6 of chapter 6, the fundamental theorem of algebra, because it's fun and you've got to be mental not to have fun with it. See, it's fun and it's mental, fun, mental. Got it. Anyway, so we're going to be looking at the fundamental theorem of algebra in this case. And what the fundamental theorem of algebra is essentially this right here. If px is a polynomial with a degree of n greater than 1, greater than or equal to 1. So you have a variable in it, one variable somewhere. With complex coefficients, remember complex numbers are anything from real numbers to imaginary numbers to rational numbers to irrational numbers and everything. Complex coefficients. Then px equals 0 has at least one complex root. Okay, it always has at least one. Now, this includes in complex roots, multiple roots, including all those, okay? Whatever the degree is, that's how many n roots there are. So if you have a degree of 7, then you have 7 roots, okay? That's including your complex, and if you multiple. So if you have a multiplicity of like 3, that counts as 3 roots right there. Those roots are also the zeros of the function. So essentially what we're looking at is that if we graph a function, and let's say it's a third degree, okay, as you see we have 1, 2, 3 zeros there. Okay. Now you might be thinking, well, I'm gonna be like, no, it only crosses at 1. Well, true, it does only have one real root. There's also complex, your imaginary numbers, which don't appear on a normal coordinate plane. And so that's the other ones that are also accounted for that count as the degrees. So let's look at this one. So how many complex roots and real roots and rational roots are possible for these? So first thing is, how many complex roots are there? Well, since it's a degree of 3, that means that there has to be at least 3 complex roots. Okay, either real numbers or real and imaginary, or imaginary, so on and so forth. How many real roots must there be? Well, you can have either 1 or 3. Okay, and the reason for that, if you remember about imaginary and irrational roots, they come in pairs. So if you have one imaginary, you automatically have to have another one. So that's why we can't have 2 real roots in this case, because then that means we only would have 1 imaginary, and we can't have that, or 1 irrational. And then how many rational roots? Or the rational roots, what it could be. This is your p over q. So you take the first or the last and divide it by the first. So that'd be 1 over 1. So you'd have plus or minus. So what you would do from here is that, again, you would use synthetic or long division. Plug in 1 and see if you come up with the actual rational, or if it comes up with a factor or not. But again, here, complex roots, the total number is whatever the degree is. Your real roots have to be an odd number. Or it doesn't have to be an odd number, but you can't have an odd number of non-roots. And your rational roots are p over q. So, look at this one. How many complex roots can we have? So you look at your degree, 6. A 6-degree polynomial will have 6 complex roots. How many real roots will it have? Okay. Well, we could have 6 real roots. Could we have 5? Well, if we have 5, that means 1 would not be real, which means it'd have to be imaginary or irrational, in which we can't have an odd number. So, because of that, we can't have 5. We would have 4, can't have 3, 2, 1. So as you see, or 0. And as you see, we would only have 0, and then the odd numbers are the only possible ones. Because if we were to take an odd number, or 0 and the even numbers, we can't have an odd number, because then we would have an odd number of irrational roots or imaginary roots. And then what are the possible rational roots? Well, you go 7, multiples of 7 is 7 and 1, and that would be all over 1 and 2. So it looks like we would have plus or minus 1, plus or minus 1/2, plus or minus 7, plus or minus 7/2. So those are your possible roots that we could have. Okay. And then from there, you would check every single one to see which one comes up with your 0. And if it does. So since we might have 0 rational or real roots, we might not have it. So looking at this one, go back to the previous one. With this one, we'll go, okay, we want to find our roots in this case. And so our roots would be 4 and -4 or 1 and -1. So we're going to use, let's say, 4. So it'd be 1 minus 5, 5, -4. Using synthetic division, 1, 4, you're adding, so that would be a -1, -4, which would be a 1, which would be 4, which is 0. So as you see, your first set would be when x is -4, x minus 4, and then you have your leftover. Now, looking at this, do we have, can we break that down? So what we would use is that we would use our quadratic formula, plug all that stuff in, because we can't think of two numbers multiplied together, get you a 1, added together, get you a -1. And so we'd use the quadratic formula, simplify it down, and as we see, we get 1 plus or minus I root 3 all over 2, and then 4. These would be our zeros, okay? These would be our zeros. So whenever x is equal to these three numbers, any of these three numbers, we get a 0. Okay. And so that's what we're kind of doing here, is that we're just kind of identifying and then proving it. But it has to agree with the fundamental theorem up here. It has to agree with this because otherwise if it didn't, then we have some problems. So that's why when we found out, okay, we've got one real root, if it didn't break down, we knew it would have had to be an irrational or an imaginary number. Okay. All right, so your IRAT, find the zeros of each of these following, these two. Okay. So again, use your any process that we used in this class so far, or in this section so far, to try to find what the zeros are. Use your calculator when needed. That'll be helpful.